Good morning, Leah. How's it going?
I'm sorry, did you say something? I stepped away for a second.
Oh, I just said good morning is all.
Oh, good morning.
Yep. Mhm. Yep. Good morning. Mhm. Good morning, DJ.
Hey, morning.
Good morning.
Good morning, Beverly.
Morning.
Good morning. So let's see. Are we waiting on anyone? I think we got Brian. I think this is our normal crew, right? Well, except for Logan. We're waiting on Logan. Let's just give him another minute or two. So, how did everyone like the meeting yesterday?
I liked hearing from the people who've taught it before.
Yeah, I thought it was helpful too, I guess. Hopefully hopefully you guys got stuff out of it.
I got a lot out of it.
I'm sure a lot of it just sounded like shop talk. So, but
I think that was nice though to kind of hear it. It's the stuff in addition to the curriculum that I think was nice to be able to hear. Outside of just the lessons and completing the lessons, like what are the other problems that are going to come up?
yeah,
The battery and brain stuff. Man, Vex. They just it's stressing me out thinking about how like, okay, yeah, I've got, exactly enough batteries to make it work, and then they'll just,
die
go
sometimes.
out.
Yeah.
Yeah.
Though to be fair, I really ever since I've been making sure to do the firmware updates, I actually haven't had a battery go out
Oh,
after.
okay.
Yeah. But definitely don't ignore those firmware updates for sure. So I think that was more of a problem early on with their
Okay.
initial rollout of, but
And maybe if it's like one battery out of 10 goes out, and because he's working with so many, maybe
Yeah.
that's why he,
has a box full of batteries.
yeah.
That's kind of scary. I think I have but yeah, it is kind of one of those things where I do order extra batteries every year just in case. So, but we use them pretty thoroughly in competition too, though. So
Mhm. I was also wondering, they were talking about how like classroom policy is you always plug in the battery as soon as you're done using it, but isn't that kind of bad battery etiquette or bad
as
battery
far as
habits?
like, yeah, because well,
like, could they be making the problem worse by having that policy to avoid the problem,
yeah, and honestly, I've never really found, well, at this point I have enough that we have spares on hand. Just so we just have the policy of just changing them out whenever we run them down.
Mhm.
We don't charge them at the end of school, but we have enough that we have spares, because between the team batteries and the class batteries, because they're not meeting at the same time or anything, so that hasn't really been a problem for us. But I mean, you can go through several class periods before having to charge those batteries. I will say, like in competition, we swap our batteries really regularly, and we keep them kind of topped up. But that's because we want to get as much performance as we can out of them. But the way that they design these batteries for consistent performance, versus, oh, I gotta let someone in. Hold on one second. Maybe instead of screws doesn't seem to be your thing, so yeah. Maybe could you sort through this and maybe in the middle over there, and just like, and if there's if there's anything that needs to be Yep. Oh yeah. So talking about batteries, compare. So I was around for the previous generation of the hardware, and so so there's been a lot of improvement, and you can kind of see the direction they were kind of going with things. Like the batteries are supposed to give a consistent performance throughout, versus like the older batteries were not smart batteries or anything like that. They didn't have any special electronics in them. They were just like battery packs of like rechargeable batteries. But like if you would get a higher voltage out of them if they're overcharged and lower voltage if they're undercharged. Well, with these batteries, they have the electronics for the battery, the voltage management. So it gives a pretty consistent, as long as you're within that operating range of charge, it gives a pretty consistent output, and that affects things like the autonomous of the robots. So that's kind of why they're like they are. But it is kind of shame, like if the electronics on a battery goes out, you can't use it again. There, and another thing too, Vex is pretty good about their RMA. Like you can send stuff back too. It's just like the batteries I had were like, over 2 years old, and at that point it was, but yeah, if you have stuff that's failing like within the year, you can definitely send that stuff back, and they'll
Okay, well,
replace
that
it.
makes me feel better. I just hearing the box of battery stores like, oh God, is this going to be a constant battle that I'm going to have to be, like we get stuff and then it goes out, like.
Yeah. And if you'll get on their tech support with them, they'll try troubleshooting a few things, because you can there's a way to reset the batteries too, like there's a, if you look at one, there's like a little hole that you can run a paper clip through to press a button to do a factory reset on it, and then you just kind of update the firmware again. It's just like if you if for whatever reason a board burns out and you can't do that, then but so there are ways to try to get a battery back as well. And anyways, I don't think it's as big as problem as he was making it out to be. But I think because he has been doing it for a very long time, and it sounds like he has like a lot of teams and things like that. And he was also doing, like, in addition to Vex, he was also doing First and all kinds of other stuff. So it sounds like he was kind of over a pretty big organization there. So he probably had, like you said, he probably just had a lot of anyways, so I guess we're all here, and our work for today will be encoder, because we're going to be doing a lot with encoders today. This we're going to be looking at Unit 8. And Unit 8 is kind of where we start kind of getting deeper into the programming. Where we're going to be doing auto straightening. That's the whole purpose of Unit 8. And so we've kind of introduced that spin 4 command, where we're driving, where the robot is driving forward a certain encoder count, and we kind of know how that kind of works. So basically, what it's doing is we're driving forward. It's actually doing a loop where it's checking to see the encoder value, and if it's less than the target value, it's going to keep on going, and then check again, and if it's still less, then it's going to keep on going, and then finally, when it reaches it, it's going to break out of the loop. And that's what's really going on when you use that spin 4 command. However, what we're going to do is we're going to write our own version of it. And the reason, and that's what like the 8.1 slides are about, is going through the steps of writing your own type of that. And the reason why we're going to do that is because, like, in 8.2 is where we're going to kind of introduce this concept of auto straightening. Like, so what's going to happen if one side veers off from the other? It's actually, this is the activity, or this is the unit where we kind of do a pre-activity, at least between 8.1 and 8.2, where whatever robots they have, I assign them and give them a couple of days to make them as janky as possible. So make it so that they do not drive straight when you tell them to go forward. And that's because we want, because if you already have a robot that's driving pretty straight, you can't really tell if auto straightening is working. So we want to have a robot that does not drive very straight. And so some things they'll do is like they'll like for instance they'll put extra friction on one side by like maybe making it too tight on one side of the drivetrain, or they'll take the bearings out of one side. That's a good one. That definitely will keep it from driving pretty straight. So one thing that can't do is change the gear ratios on each side, because the encoders won't know that the gear ratios are different. So that's one thing that they can't do to make it drive funny. They still have to kind of use the same gear ratios on each side, but they just have to make one side jankier than the other, or something. And because otherwise, the robot's going to drive pretty straight on its own. And what we're looking for is a robot that doesn't drive straight, and then we're going to correct it through our code, and that's kind of the point. So, and honestly, the kids have a lot of fun trying to build a robot as bad as possible. So I think that will be kind of like a fun break for them between the hard coding stuff. So let me share my screen for a second, and let's briefly kind of look at the 8.1 and 8.2 slides for a second, just to give kind of overview of those. So the 8.1 slides are kind of where we're introducing loops. We're also introducing like in chapter 8, like a conditionals, like the if statements and else if, else statements. But mainly the 8.1 slides are about doing loops. And in particular, doing a while loop. And for those of you that kind of new to this, so what a while loop is basically, this is the setup for a while loop. You say while, and then in the parentheses, you have some sort of condition that's trying to be met. Like, so like while X is less than 100, or while blah is true, or you could, if you wanted like an infinite loop, you could just say a while true, or while 1 is equal to 1, and that would always be true, so it would run forever. But the idea being is that as long as that condition is evaluating to true, it's going to repeat what's in between the curly braces here. And then once that condition becomes false, then it's going to kick out of it and then continue on with the rest of the code. So that while loop kind of just keeps repeating over and over and over and over again, as long as this, whatever your condition is, remains true. It's just going to keep repeating over and over and over again. And then finally, if this ever becomes false, then it will kick out. So like in your driver code for your robot, you pretty much have like, if you're doing like competition or whatever, you'll probably see in the driver code. In fact, let me just pull up. I'm going to load up the template to use for competition real quick. Templates. It's kind of broken up into these different sections. So it's got a pre-autonomous section, autonomous section, and a user control. But you see in the user control, they have this while true, and anything you want to do, like with the joysticks or the buttons or anything like that, to control the robot, you're going to put inside this while true loop, and that way it can check over and over and over again. Because if it's not in a loop, and you say maybe you have a code, or you want a code that says like when you press a button, it's going to raise the arm. So if you have that code and it's not in a loop, then what that means is it's just going to check right then that first time through, when it's running through the code, and after that it won't ever check again. But if you have that, if you press a button, it'll raise the arm. If you have that in a loop, then it's going to continue to keep checking over and over again to see if you ever press a button. So it won't just check that one time. It's going to continue to check over and over and over again. So we're going to kind of be using these loops today. Here is basically a flow chart showing this kind of loop here. And in this case, this is the spin for command. I think we looked at this flow chart before, but basically what's going on when you run spin for is, and are you guys familiar with the like flow charts and like, like how a diamond is for a decision that's being made, and the square blocks are like your actions. Does that sound familiar to people, or is anyone new to that? Or
It's ancient to me, but I don't recall the explanation for the diamond, so that does sound new to me.
okay, so in a flow chart, when you have a diamond, that's where like some sort of decisions being made, basically. So in this case, it's asking the question like, is the encoder value less than X? And if it is, that's where the paths branch off. If it is, it's going to go this way. If it's not, it's going to go this way. And so that's kind of how that's kind of just the symbology for flowcharts. And I think in the engineering class, I get into flowcharts too, right? Anyone teach an engineering class?
Yeah, we talk about that process flow charts like in chemical engineering. They have them, and they even go through like an Arduino coding lesson. Now I'm gonna have to probably redo it because like in that class, I don't mean to talk about it too much. In the computer science class, they make the kids program, but we don't really teach them a ton, so they're like completely clueless. So
Yeah, are you talking about the ICT class or?
No, I'm talking about intro to engineering.
Oh, yeah,
Yeah.
that's true.
Yeah.
Because my kids, my ICT kids take intro, and so when they get to the Arduino stuff, we actually kind of take a little time in the ICT class to kind of go over some of that, because it's just not a lot of, I guess not a lot of time is just spent on it, maybe.
Yeah. Well, when I talked to a couple people who teach it around here, and I've talked to Vanessa. What I'm probably gonna be doing is there's a first semester like Arduino component, and then there's a second semester Arduino component, and I'm just gonna probably put them together and just kind of use it as a time to teach them for like a month on how to code, because it didn't work very well. Some kids would take the time to do it, and you could find the code online and stuff, but it just wasn't enough. So
Was that the activity where they did the Morse code, or is that
yeah, it was like spell your name, Morse code. A lot of it's really repetitive if you don't, unless you know how to use like other commands and stuff. But then whenever you get to the second semester part, they are required to use if loops and stuff. So
yeah,
I used for the conveyor belt project, I had them add motors, and that's where I was able to kind of make, I mean, because a conveyor belt is just a robot flipped on its back. So that's what we did.
okay, yeah. And a kind of a cool project would be like if you incorporated like the optical sensor or something like that with a conveyor belt, and depending on what color objects on the conveyor belt, it might do something or another, like maybe an arm to kick red things away and let blue things through or something. But at any rate, okay, so what we were saying is just that diamonds just mean that a decision is being made, and that's where the paths can branch off. Now, in this case, we can see that, so what's going on here is the encoder value less than X? If it is, then yes, it is. Then it's going to drive forward. And then it and notice the arrows kind of go back and back in on itself. So this is this is showing a loop here in this process. So it's going to drive forward, but then it's going to come back, and then it's going to go right back and check again. Is it still less than X? If it is, then we'll just continue to drive forward, and we'll keep on doing that until hopefully eventually it's going to return a no. So like when your value finally gets greater than X or equal to X, it's going to return a no. And at that point, it's going to follow this branch, which is stopping the motors and then ending the program. So that's kind of what's going on with this flow chart here. So you'll see these decisions or these diamonds, you'll see them for loops. You'll also see them for like if statements, which we'll also talk about, I think, in 8.2. So here are some of the condition things you can use. So you can use like less than or greater than, or less than or equal to, or greater than or equal to, or is equal to, or is not equal to. One comment I would kind of like to make, and it's kind of pointed out in the ICT class, at least when they talk about conditionals, equal, you kind of want to, unless you're dealing with an integer or a Boolean values, you kind of want to avoid using equal to, simply because, well, you don't want to use equal to with floats or doubles or anything like that, because when we're saying equal to there, we're meaning like exactly equal to. So if you have like, let's say, like, okay, for instance, let's say you're trying to say something is equal to 3, and then like you end up with like 3.00002 or something like that. So it's pretty much equal to 3, but it would not consider that equal to 3 because it's not 3, it's 3.002. So there is another, you can do about equal to, and I think it's the tilde equal, I think, or it's equal tilde. It's one of those or the other. Does anyone remember off the top of their head? Not really. Okay.
The tilde probably would come first, if anything.
Oh yeah, I think it is. Because like not equal to, for instance, has the explanation for it first. But I think that is one that you can also use. And when you say it like tilde equal, that's about equal to, and that's equal to within, like, I can't remember how many decimal places, but it's like within like 5 decimal places, something like that. It's equal.
Is that
Okay.
a C++
Yeah.
thing, or is that something built into the Vex library?
I think that's a C++ thing, if I'm not. Let me look it up. About, what would it be called? About equal? Maybe it's not. Now that I'm thinking about it, that might have been just something Fernando made for
Yeah,
that other language.
Yeah, I'm not seeing
I
anything.
think you've got to write your own code
Yeah.
to make that kind of comparison.
Okay, never mind. So don't worry about equal. That was just something from ICT, and that was just something Fernando wrote, I guess. Yeah, I don't. Okay, so I guess I would just mention you probably want to use equal for integers and Boolean, but be careful about using it for floats or decimal points. Anything that would have decimal values. Okay, so this is what's kind of known as, well, this is not really not a really fleshed out one, but this is kind of like a truth table, right? So here's just some examples like of using equal and not equal. So 75 is equal to 75. That's going to evaluate to true. 100 is equal to 75. Well, that's not true. So that's going to evaluate to false. So one thing to make sure to point out to the kids is there is definitely a difference between equal and just one equal sign. So if you have just one equal sign, that's what's known as an assignment operator. And so that's where you, like, so you say X equal 10. What you're doing there is you're assigning the value 10 to X. So if you just have one equal sign, that's where you're actually just assigning the value to that thing. On the other hand, when you have equal like this is a comparison operator. This is actually checking to see if it's equal or not. And then it's going to return a value of true or false, depending on if it is actually equal or not. So this is just kind of showing, like, 75 is not less than 75, so it's going to return false here, right? And 100 is less than 75, so it returns true. So this is just kind of showing those comparison operators. So like in this case right here, this would be one way to kind of use that. So if we're saying while, and then inside that, we're saying while the position of the left motor in degrees is less than 1800. And so as long as that condition is true, you're going to do the stuff you have in your while loop. And when this condition no longer is true, like when it gets greater than 1800, then it will kick out of the loop. So and then if you wanted a loop to run forever, you could do something like this, like while 1 equals 1, because 1 will always equal 1. Or you could just say like while true, because true will always be true. And that would be a way to make something run forever. And here we are kind of getting into like, so that motor position is actually going to be changing as the motor turns, right? So as the motor's turning, the encoder values are counting up or counting down if it's driving backwards. And so that's going to, if we have that in a loop, it's going to be constantly checking that and seeing if it evaluates to true or false. Let me think about what this is referring to. Okay. It's also what it's kind of doing here is also kind of talking about accumulated error. Like, so like, let's say like your motor slips for whatever reason, and so your turn isn't or you're going forward didn't go as far as you wanted it to, or something like that. Let's say let's say you were trying to do this, like, so these are like, you calculated that, okay, to go forward my desired distance, I need the motor to rotate 1800 degrees, and then to do the turn I want to do, I need the motor to rotate 700 degrees, and then to do this last forward distance, I need the motor to go 2200 degrees. So what would happen if, like, say, let's say let's look at this. Let's say it overshot for whatever reason, and it ended up going 1900 degrees. Okay, so what's that going to mean is, okay, so like in this case right here, going back to this, we know we're gonna, if we're starting at 0, we know that by the time we're done with this leg, we would want it to have gone 1800 degrees, right? And then we know that by the time we get done with this part, the turn part of this, we would have wanted to have gone to 1800 plus the 700, right? So at this point, after we've completed the turn, it should be at 2500. Is that right? Yep. Yeah. So at this point, we should be at 2500. And then finally, at this point, we'll have gone this 2500 plus this additional 2200. So by the end of this, we should be at 4700. However, what could happen is, let's say we were trying to go 1800, but instead it went 1900 before it did the turn. Well, if we are just if we are just trying to now just go by 2500, what that actually means is, instead of like doing this 700, we'd actually only do 600, right? Because we've already gone to 1900, so what's left over is 600 left. I guess they're showing another overshoot here too, but even if it didn't overshoot to 625, if we were just going by 2500 for the next part, it would only turn 600, so it wouldn't turn as far as it needed to. So the point they're trying to make here is, like, when you write your code for this, it's a good idea to go ahead and actually reset your encoder back to 0 each time, like before you do it. Because so what you could do instead, and this is showing. Okay, so so this is showing it was off by that by less than 100, but it was also kind of still off. I don't know why. That feels confusing in this slide though, because this is kind of like combining two different sources of error together, right? Because what you're trying to demonstrate here is that this turn is going to be off because you went further with this, and so you have less left over to do with this, right? So I don't understand why they would want to also throw in this overshoot here, because I think that's just kind of conflating things, I guess. So here, because in this other one, they're actually kind of showing that you did reset it. So it went 1900 degrees, but that's okay because we're going to reset it. And then it's supposed to go 700, but I guess it's still overshot. So so now it's turning 725 degrees, but at least is closer to that 90-degree turn that we wanted versus like this. So even if there was still some overshoot, that's kind of what they're showing here. And so to reset the position of an encoder, this is a command you would use. It's just set position. And then and that will just reset that value. And you can set it to actually whatever you want. But if you just want to reset it back to 0, you could just say 0. But it's a good idea to do that after each leg of what you're doing, is to go ahead and reset the position back to 0 for each of the motors. And so, well, let me just kind of look through the rest of this. There is also, we can talk about compound conditionals, like if you want to check multiple conditions. And that's where we have these compound statements, like the and statement and the or statement. So for instance, when we're trying to go a certain distance, one thing we could do is check both encoders, like the encoders on both motors. So like, for instance, we could check to see if the left motor encoder is less than 100 and the right motor encoder is less than 100. So that way, and that would only return true if both those statements were true. Or we could check to see if the left motor encoder or the right motor encoder was less than 100. And in that case, it would return a true if either of those were true. So just to explain how that works, and is only true if both parts of it is true. So if both the left and the right side of the and are true statements, then it will return true. However, if either one of those statements or both of those statements are false, then it's going to return false. So in order for an and to return true, both statements have to be true. On the other hand, with an or, if or will turn true as long as at least one of the statements is true. So if this side is true and this there's an error in this slide, isn't it? So this is actually supposed to say yeah, these are all. Let me fix this now that I'm looking at it. Okay, yeah, those. So that's how you do an or. It's these double line here. So as long as at least one of the statements is true, or will return true. Now I think, if I'm not mistaken, in Unit 8 homework, I think there is a truth table on it. Yeah, this right here. So just to make sure that we understand these truth tables, okay. So how many of you have seen a truth table before and know how this works? Brian has. Dennis probably has. Beverly, you have too. And by the way,
I don't
guys,
recall.
you have not seen this before. Okay. I think it might be worthwhile if we kind of try to work through this together and see how well we do with this. Does that sound good?
Yes.
Okay, so what we're going to put here in these boxes is either true or false, and we can just say T or F. So here is the X values, here's Y values. So like for this first row here, it's saying X is 10 and Y is 11.
Hey, hey, Eric, can you zoom in a little bit on your screen?
Oh, yeah. And also, if you just want to open up yourself, this is the Unit 8 homework. Yeah, let me zoom in a bit. Oh, what's going on? Is that, let me know when it gets, is that big enough?
Much better, yeah.
Okay, I can go a little bigger too. Okay, so let's see. Anyone want to volunteer to kind of walk through this first table here? Okay, so Leah. Okay, so this first part, X is less than or equal to Y. Is that true or false in this case?
That would be true.
That would be true because 10 is less than 11.
Mm-hmm.
Okay, Y is greater than 5.
That would be true.
Okay, so that's also true. Okay.
So for this one, it has to be both of them, right?
Yeah. So in this case,
That
we
would
have,
be true
Yeah.
as well. Well, it would be true. Yeah, it's going to be true all the way across.
yeah, so this is going to be true as well. And that's because this was true and this is true. And for an and to be true, they both have to be true.
Right.
But both of them were true. Does that make sense, Beverly, so far?
Yes, I understand.
Okay. What would and
That
then
would be true as well.
yeah, this would also
Because
be
both are, even though only one has to be, correct?
yeah.
Yeah.
So or is true as long as at least one of them is true. Okay, so this would also be true. Okay. How about Beverly? How about you take the next one then? Yep.
Okay. Would it be false because you have that less than, greater than? If it was just an equal, then
Well, so that symbol is less than or equal to, is the way that reads. So it's
since it's or, then it's still true.
yeah. So
Oh, okay.
yeah, because that's less than or equal to, and since 4 is equal to 4, yeah.
Okay.
Okay, what about this part?
False.
Yep. Okay, how will this and evaluate now? If one is true and one is false.
Okay. It'll be false.
That's right. Because and is only true if both are true.
Okay.
And then how will this or evaluate?
Because it's or is still true.
That's right. Because or will evaluate to true as long as at least one of them is true.
Okay. Got it.
Yep. Shall we, anyone want to walk through this other one? No volunteers?
Yeah, I'll go.
Sure.
100 is not less than or equal to 90, so false.
Okay,
90 is greater than 5, so true.
okay,
Since one of those is false, the and statement is false.
okay,
And since one of those is true, the or statement is true.
yep. All right. And then we have this last one here. Anyone want to try it?
This one's gonna be the same as the one above it. Well, no, it's, yeah, this one's gonna be the same as the one above it. Or no, it isn't. They're gonna be false, false,
So false,
Um,
false.
false,
Okay,
and false. Yeah.
yeah. This time, since there wasn't anything true, so the or evaluated true. Yep. I mean, evaluated false because they were both false. Okay, let me delete all of that because this is like the actual. We don't want to give the kids all the answers.
I do that all the time by accident. Like the next class period gets all the right answers because
Yep.
I typed in it all.
Yep.
And if they've never typed code before, they probably don't know where that vertical line is on the keyboard.
Yeah, that's true. I do have to point that out to them because it's not something they use very often, right? I can't think of an English class or anything like that.
Yeah.
Having a reason to use that. Okay, so back to our slide. I'm gonna because that just makes everything. That actually makes it when I have the zoom cranked up, it makes the slide smaller. No. Okay, so that's how those truth tables work. Now, in our case, so we have kind of an option here of if we're using both motors like the left and the right side, we have an option of either using and or and they're going to do two different things depending on which one you use, if you use and or and what would end up being better to use, well, and that actually kind of depends on your situation. So can anyone tell me the difference of what's going to happen with these? So like say if the loop is to go forward as long as these conditions are true, or as long as this values are true, what's going to be the difference between these two?
With the and statement, both of them have to be true. With the or, only one has to be true.
That's right. So how's that going to affect the behavior of the robot?
I feel like the and statement, like if there was some veering or something happening, that it would just stop. It would just stop the robot. Versus the or statement, it would continue going, but the error would continue veering. Is that correct?
Not necessarily. It is kind of true because it is true that these might get off, right? Like one side might get off from the other side, right? But let's say so let's think about that. Let's say if the left was ahead of the other, at what point is the robot going to stop? So with our and,
When they're both.
So wait,
they'll
would
stop.
oh, go ahead.
would the and kind of auto correct because it's getting them both even, where like the or one can be more than the other? Does that make sense? So like the and's going to keep going till they're both the same. Is that not correct?
Well, okay, so and is going to keep going while both of them are less than 1800, right? So as soon as one of them reaches that 1800 value, then it's going to kick out of the loop. So if one is ahead of the other, then as soon as that one that's ahead reaches 1800, then it's going to kick out a loop. So in the case of and, it's gonna run until at least one of the motors, until one of the motors reaches it,
Isn't that
and
what
then
DJ
it's gonna
said?
kick it. And go ahead, Logan, sorry.
Isn't that what DJ said? Like I said.
Yeah, I guess that's what I was kind of thinking, but maybe I said it wrong. I don't know. I'm not sure if I explained it the way.
Okay, well, yeah, maybe so.
I guess what I was thinking was that like, so like if error starts to occur and one motor gets ahead of the other, then it's going to hit that 1800 first and it's going to stop. Versus if it's an or statement and they get off, it's not, it's going to, the robot's going to continue. It's going to continue until, I don't know. I'm
It
Okay,
just takes
well,
one of them to stop on the on either one of them.
so yeah, in the case of the or is going to continue the value to true until both those statements are false. So what that means then is it's going to keep on going until both the motors hit that threshold, or both sides hit that threshold. So so in one case, in the and case, you're going to keep on going until at least one of the motors reaches 1800. But in the or case, you're going to keep on going until both the motors hit 1800. So in the case of one getting ahead of the other, it's going to keep on going until the one that's behind also reaches it too. So so that's kind of the difference there. And you can kind of do both ways depending on what you're trying to do. But probably the most common thing to probably do would be use the and, because you just run until at least one of them hits it, right? And that's what it would happen with the and, because as soon as one reaches that threshold, it's going to return a false on that side, and that will make the whole thing false, and that will kick you out of the loop. On the other hand, if you're using an or, it's going to wait around until both things return false before it kicks out of the loop. So so you might run into a situation where one side just can't reach it. Like maybe it got stuck on something, and it just can't get to 1800. In that case, it's going to keep on trying to go until it reaches that 1800. Whereas with the and, as long as at least one of the motors reaches it, it's going to kick out. So that's kind of the difference between using and or in the case of a robot going forward. So yeah, so the and is going to go until at least one condition returns false, while the or is going to keep on going until both conditions return false. So, and this is just kind of talking through that situation. So what if you want to write it so that your robot goes in reverse? So what's going to happen with the encoder values if you're driving backwards?
They would be negative.
That's right. They're going to be counting downwards, and so you're going to get negative values there. But that would be kind of a problem if you just have it like this, because like, let's say you're trying to drive backwards. Your encoder values are going to be negatives. Are you ever going to reach 1800 that way?
Unless two numbers are negative, creating a positive. I'm just guessing.
Yeah, because if it's going backwards, it's just going to continue doing negative numbers. So it might reach like negative 1800, but that's still less than 1800. And so you're never, if it's driving backwards, you're never going to reach that value. So how can you get around that then for going backwards?
Can a value be higher to where when they both spin backwards, somehow the higher number is a positive, which will cause it to have an 1800, but because I don't know. Am I
Would you do
getting
like, can you do negative numbers? So could you do greater than negative 1800?
Yeah, you could do greater than negative 1800. That would work. It's just that in that case, you would need to keep in mind because you would have to flip the sign around, right? It would have to be greater than instead of less than. And then you would kind of need to have a different conditional depending on if you're going forward or backwards, right?
so it's like saying 36, a positive 36 versus a negative 18 or something like a positive what 39? You know what I'm trying to say. Double that number, but the higher number it will be a positive, causing it to still reach a positive.
I mm, uh, I don't think that would be the way to go about those of you who are math people, is it any way to make a negative number a positive number? What is a math thing that you do?
Absolute value.
Yeah. So what we could do is instead of just using the left motor position or whatever, we could just take the absolute value of that left motor position. And that way it doesn't matter if it's negative or positive, the absolute value will turn it into a positive. Because that's what absolute value does. So like the absolute value of negative 10 is 10, or the absolute value of negative 30 is 30. Or the absolute value of 30 is also 30. So what absolute value does is if it's positive, it'll keep it positive, but if it's negative, it'll turn it into a positive. And so in C, we do have a function for that. And it's this function right here, FABS. That just stands for function absolute value. And so basically to use it, you would just say FABS and then of whatever you wanted. So like if you said FABS and in parentheses 100 or negative 100, it's going to take the absolute value of whatever it's inside. So in this case with the motor position, if we say FABS, it's going to return an absolute value of that. So even if you're spinning in reverse, it's going to, so let's say it got to negative 1000, the absolute value of that's going to be 1000, right? So, now in that case, it's still less than 1800, so it's still going to return true, which means it's still going to run the loop. But if we got all the way to negative 2000, well, the absolute value that's going to be 2000, and that will be that will no longer be less than 1800, and that will return a false, and that will kick us out of the loop. So so we'll be using this absolute value function on our motor positions when we're doing this kind of stuff. And so if we put it all together, let me see. Let me see what we got here. Yep. So this is code for just driving backwards. And so what we've got here is first we're resetting the positions of the encoders. So we're setting them back to 0. And then we've got this loop here where we're checking both the left and the right sides, and we're using that absolute value. And then we're spinning in reverse. And it's going to just keep on spinning in reverse until one of these conditions is met. So until it gets like equal or greater than 1800, it's going to keep on spinning reverse. I guess the only thing missing from this code is outside of the loop, you would also want to stop, a left motor stop and a right motor stop, because otherwise you're not ever telling the motors to stop, even after you exit the loop. So so these lines of code are kind of equivalent to doing the spin 4. So why go through all this work when we can just use one line of code to spin 4? That's probably the question that your kids are going to ask too. So why are we doing all this extra work when we just got that spin fork command? And that leads us into lesson 8.2. So lesson 8.2 is so why are we going through all this? And it's because we don't have to only do spin here. We can do other things inside this loop, right? This, besides just spinning it, we can do all kinds of other things. Like we can change like the motor velocities or all kinds of other things like that. So that's and that's where we kind of get into this idea of auto straightening. So let's say let's say you had a wagon hooked up to this situation here. Is that gonna probably is that wagon probably gonna go straight? Well, yeah.
Do the oxen have encoders?
Yes. Well, even if
Oh, I guess it's an ox and a donkey, huh? I see it
Yeah.
now. No.
Yeah. Well, and it is kind of true. I mean, these are smart, intelligent animals, right? They might be used to walking together, right? But one side is definitely stronger than the other. So that stronger side is probably going to pull to that direction, right? And so the same thing can happen with your motors, whether due to like friction or it could be just one motor is like brand new and the other motor is an older one or something like that, and so they have a different amount of wear or so there's all kinds of reasons why one motor might not spin as fast or as far as the other motor. And if that's the case, what's going to happen is your robot's going to veer one direction or the other, which is kind of what we'd see like here. So like, for instance, if one side is going slower than the other, then like, for instance, if the left side is going slower than the right side, then what's going to happen is that right side is going to be traveling further, and that's going to make the robot drift to the left. On the other hand, if the left side is going faster than the right side, then it means its encoder count's getting higher, and that's going to cause it to drift right. And if they're both equal to each other, then it's going to just be driving straight. So what you could do to try to correct that, for instance, is by having the motors go at different speeds. So like, here's some corrective action they're mentioning here. So like, for instance, if we're drifting left, that means that our right motor needs to catch up. Oh, no. Did I get that right? Ooh, no, this is left. Okay, if we're drifting left, that means the left motor needs to catch up because the left is less than the right. And so if that's the case, we want to make the right motor spin a little faster than the left motor spin a little faster than the right motor. I'm left-handed, and I think that's so I oftentimes get my left and rights confused just by being left-handed sometimes. So I'll oftentimes get this mixed up. But if we wanted, so if it was drifting left, the way we would correct for that is making the left side go a little faster. And so we could do that kind of in code where we're saying the left motor is, say, maybe going 50%, while the right motor is spinning at 40% speed. Or if it's going straight, then we'll leave them both going at the same speed. Or if it's drifting in the right direction, well, that means that we need to speed up the right side. And so that's why we will have the rights going faster than the left. So these are three situations we can have. We can have it's either drifting left, it's going straight, or drifting right. And so what we can do is in our loop, instead of just saying motor spin, we can actually make adjustments every time we go through the loop. And that's where we kind of introduce these if statements as well. So an if statement is just kind of like with a while loop. If statement, you feed it a condition, and if that condition is true, then it's going to run whatever's inside that squiggly. And if that condition is false, then it's just going to skip it and not run it. So the difference between like a loop like our while loop and this if statement is an if is only going to run one time. It's going to either going to if the condition is true, then it's going to run this code and then move on. If it's false, then it's just going to skip this code and then move on. But either way, it's moving on and it's not coming back. So that's why what we're going to see later is we're going to embed these if statements in that while loop. So that way we can run through all these conditions and do different things. And then the while loop will have us repeat and go through all these conditions again over and over. So, so we could have just a series of ifs. So we could check to say, like, if the left side is less than the right side. And then we could check, like, if the left side is greater than the right side. And then we could say, like, if the left side is equal to the right side. And so, like, if the left side is less than the right side, then we would have the left side speed up. Or if the left side is less than is greater than the right side, then we'd have the right side speed up. And if they're equal, then we'll have them go the same speed. However, that's not really from a processor kind of point, a computational kind of thing. That's not really the most efficient way to do it. And the reason for that is because some of these statements are mutually exclusive, right? Because, for instance, if the left side is less than the right side, then there's no way that the left side can be greater than the right side in that case. And also, if the left side is less than the right side, then it also means the left side can't be equal to the right side either. So the way this is set up, every time it goes through the loop, it's going to check these three conditions. So even if the first condition ended up being true, and we know that these will be false, it's still going to check anyways. Which means you're doing, like, 3 times the checks, right? Than you would need to do. Like, if there was another way to do this, we could maybe just check just this one thing. And that's where and that's what we want to do instead. So that's where we come into talking about so this is just showing those ifs at work. And so this would be kind of like the code for doing those ifs. So this is not this is probably not the most efficient way. So okay, but so first is checking if their two are equal to each other. And if they are, they're going to go at the same speed. Then it's checking to see if one is greater than the other. And if the left is greater than the right. If the left is greater than the right, that means that we want the left motor to go slower than the right. And then it's checking to see if the right is greater than left. If the right is greater than left, then in that case, we want the right motor to be slower. And then it's going to go through the loop and then check all over again. And then it's going to keep on doing this until we reach our target value. So this is kind of like our or spin 4, but now it's also got this kind of auto correcting to make sure it goes straight as well. So what do we, okay, so this is kind of talking about mutually exclusive stuff. So here we have, for instance, whole milk, 2% milk, I guess this is 1%, and skim milk. If you know your milk is whole milk, then you know it's not 2% or 1% or skim. So so these are kind of mutually exclusive things. So if you know your milk is skim milk, then that means that it's not whole or 2% or 1%. And so you can use another thing called else. So instead of just an if, what an if does is it will run the code if the condition is true. Otherwise, it's going to skip on. But if you have an if and an else, what goes on there is if the condition is true, it's going to run the part between the squigglies for the if. Otherwise, if it's false, then it's going to run something else. So that way you're running code whether it's true or it's false. And so instead of just like running code if it's true and not doing anything if it's not true, when you do if and else, you're going to run some code if it's true, but you're going to run some other code if it's not true. So you're going to run code either way with an if else statement. And then in addition to that, if you have multiple like mutually exclusive things, then you can have this if and else if and else. And you can have as many else ifs as you want. So like, for instance, you can have a situation where like, if X is greater than 5, else if X is greater than 4, else if X is greater than 3, else if X is greater than 2, and then else for like your last thing, if you wanted to. So, and that way, you would hit all those kind of conditions, and it would check the first one first, and then if that wasn't true, then the else if is going to check for the next condition. And then finally, if none of these were true, then it would finally run the last part, the else. So the else is kind of your catch-all for if any of these other things weren't true. Then finally, it's going to get down to the end and run else. So I personally don't think this is the most efficient way ordering of this. What do you guys think? Because right now they're doing if the left is equal to the right, else if the left is greater than the right, and then else. So this final else would be if this wasn't true and this wasn't true. So the only remaining option there is if the left is less than the right, right?
Wouldn't it be pretty unlikely that the two encoders are actually equal to each other?
That's what I think as well. That situation is not going to come up very often, right? So that would be probably my else. I would probably have, because it's always going to check this thing first, and then it's going to check the second thing if the first thing wasn't true. This situation of the two being equal is not going to come up as often as these other situations are going to come up. So in terms of efficiency, you would probably want your most likely condition to be checked first, and then your next most likely, and then finally like your least likely condition should probably be your else. So it's kind of like do you guys ever play Guess Who when you were a kid? Yeah. So usually you would try to ask questions that would eliminate as many choices as possible, right? Well, I guess it depends on your strategy. Some of you might like go for that lucky play of I don't know, of one that if you were right, then you pretty much knocked out everything but a couple left, right? And that's kind of what this is. This is like running that lucky play. Is like, this is not going to happen very often, but if it does, then yeah. But there is a better order of doing these. I I don't know if you want to, if you have to get that deep with your intro kids, but I like to kind of talk about that kind of stuff. Because there's not everyone's going to get that, but there's going to be some kids that do get it, and they do, and they'll appreciate it at least.
I mean, I think it's important that, I mean, the whole point of teaching this is to teach efficiency in code. And so this is a teachable moment here to, you know, I don't think it's that far off to it's worth going into.
Yeah. Beverly, you are, you know, you would probably be our sounding board for like a student perspective, I guess, because this coding stuff is kind of new to you guys, or new to you. So you would be the closest that we have to a student perspective. How confusing is this so far?
Okay, so let's see. Looking at it through their eyes, I guess sometimes just, I don't know, I'm thinking just the abbreviation itself. And I think sometimes a student would need to see it all spelled out, which it should be to the left here where it says use if the options are mutually exclusive. And sometimes I notice my students, because we try to work on their skills with reading and understanding, and we do have a lot who do not know how to read, so they act out because they're trying to cover up. So wanting to know what the word mutually means, you know, can be a factor, or even implementing could be a factor, let alone with looking at these different symbols like the double parentheses, or, you know, so it's what creates it to be more foreign is if they do not have a good vocabulary as well.
Yeah, that is definitely true. Yeah, and so, and I'm obviously kind of covering this faster than you would cover it in class, right? So, and that's because my audience is different than what your audience is going to be. So we're all educated adults here. So I'm able to kind of go over this a little faster, but but it's definitely true, like you said, and I've run into those situations too, where there's a lot of the vocabulary, and you kind of need to take the time to explain those concepts. Like, for instance, back on this slide, about the idea of like mutually exclusive, what that means, if one of these things is true, that means nothing else is, everything else is not true, right? So like if it is skim milk, then it can't be whole milk, because that's mutually exclusive. If it's one thing, it's not the other thing. It can't be tea and not tea at the same time, right? That's a Hitchhiker's reference, but no one caught that. Oh well. Okay, so okay, so so this is kind of putting all that code we're talking about together here. In this case, they actually do have it rearranged so that they're checking like a greater than or less than. So this is putting everything together in the last few slides. So we got some variables here that we've set up for a fast speed and a slow speed. So we have and then we have a distance, whatever distance we're trying to reach. And so the first thing we're doing here is we're resetting the encoder positions. And then what we're saying is, and we're using the absolute values for these. So while the absolute value of the right motor is less than that distance, and the absolute value of the right motor is less than that distance, then it's going to run this loop. So it's going to continue running that loop until those encoders, the absolute value of those encoders reach 500. And since we're using absolute value, that means it doesn't matter if it's going forward or backwards. Because either way, it's going to be generating positive values there because we're using absolute value. And then here we have our three situations here. So if it's less, if the right is greater than the left, then that means that we want our right motor to slow down and our left motor to speed up, because the right motor has got ahead, so we need to slow that one down. So that means we're going to run the right motor at the slow speed, and we can adjust those speeds by adjusting these variables. And we want the left motor to go by the fast speed. Otherwise, if the right motor is less than the left motor, that means the right motor needs to speed up and the left motor needs to slow down. So in that case, we'll run the right motor at the fast speed and the left motor at the slow speed. And then finally, if neither one of those conditions is true, then what that really means is that then they're both equal to each other, because and if they're both equal to each other, then we want to just run them both at the fast speed. And the only thing I would probably add to this code is at the end of the while. So this while loop, okay. So the while loop, it opens the curly brace here, and it's going to end it here. That's one thing about troubleshooting their code, is checking their curly braces. So we have open curly brace, and then another open. So we have two open, because it opens for the if. Now it's going to close for the if. So now we only have one open. Now we're opening up another one. So now we have two open. Now we're closing it off. So now we're back down to one open. And then we're opening up another one. So we're back up to two open, and then we closing it again. So we still have one open. And then finally we're closing it off here. And that closes them all. So that's gonna so what this is gonna do is it's gonna run this while loop. And then when it kicks out, the only thing I would add is I would have like a left motor stop and a right motor stop to make sure that the motors stop after we're done running this code, or after we're done out of this loop. So this would be some auto straightening code for going forward a certain amount. And these are some different situations here. So if we wanted to go backwards, we could just change all this to reverses, right? And this is assuming that the 500 ticks was enough to go 2 feet forward, by the way, or 2 feet. So if we wanted to go, if we wanted to travel further, like 4 feet, we could just do 2 times the distance here, or we could just do, we could just change this distance to 1,000 if we wanted to as well, right? So just a summary of our conditions. So a while loop is going to run, and it's going to continue to run over and over again as long as the condition is true. So it's going to keep repeating over and over and over again. If is going to run the code if it's true, or it's going to just skip by and not run it if it's false. But it only goes through that once, unless you have it embedded in a loop, and then it can run through it multiple times. And then finally, an if, an else if, and else. That's so if the condition is true, it's going to run this code. Otherwise, it's going to move on and then check to see if this next condition is true. And if it's not true, then, or if it is true, then it's going to run this code. And you could continue to have more and more else ifs if you wanted to, where it checks another condition. And then finally, if none of these other conditions were true, then finally it's going to run the else. And notice there's no condition on else or anything like that, because it's just going to run if none of these others were true. So finally, if none of these were true, then it's going to run the code in else. And so you would use these in mutually exclusive situations. So
I'm trying to think how a student would think now. So when you mention if something were to be true, then it would run the command. But when you say else if, that means just like previous, you had showed if there was a true or false, correct? And then
yeah, so the else if is only going to be run if the if was false. If the if is true, then it's never going to run any of the other stuff. So so you can run into situations like okay, let's say you I'm trying to think of a situation here. Okay. Let's say you wanted to run something if X was 5 and you wanted to run something else if X was 4, and if you wanted to run something else if X was 3, and you want to run something else if X was 2 or something, and so forth. So you want to run different things, whether it's like 1, 2, 3, 4, or 5. If you ordered your conditions wrong, you could end up in a situation like, for instance, let's say our very first if in that situation was if X is greater than 1, or yeah, or no, how about we instead say if X is less than or equal to 5. So if and let's say X was 4, well, 4 is less than or equal to 5, so that would be true, and it would run whatever you have here. But then, like, let's say we had like another condition where it was like X is less than or equal to 4. Well, it will never run that condition because it's already run the condition for X being less than or equal to 5. So since that was true and that one ran, that means it will never get around to running the other ones. So it does kind of matter the order that you put your conditions in sometimes, if that makes sense, and it might not make sense. So what might be good for us, and I will say this, just going through the slides and explaining to the kids is they will still most likely be lost, just even if they have the notes in front of them. What really makes it click for them is to actually try writing some code together. And it doesn't necessarily have to be the code from the assignment or anything. But we could write, but for in our case, let's give me 1 second to I accidentally closed my folder. Let's look at what our assignments are in 8, and let's maybe try writing that code together. Spam. What am I doing? Okay, I'm almost there. So let's look what this first activity has us do. Well, let's actually do the harder one. Let's do the 8.2 activity. So the 8.2 activity is basically doing the basketball drill again, but this time also including this auto straightening code to do it. Fortunately, at this point, we haven't introduced functions yet. The functions would make this code a lot simpler. I actually go ahead and kind of introduce a functions because otherwise the code gets really, really, really long, and it's really just a lot of copy and pasting at that point. But I think functions actually gets introduced in the next unit. But if you want to kind of go ahead and introduce the concept of a function to them too, I think the reason it's kind of spaced out is because they're already kind of being overloaded with these loops and while statements and stuff. So introducing making a function, if they're not used to it from their other classes, might also be a bit of a stretch. But let's try tackling this. Do we want to go through that situation where we have someone do the code and maybe talk them through it? Last time Leah volunteered to do it, because Beverly, since you don't actually can't share your screen, it's kind of hard for us to see. But does anyone want to try tackling writing some code for this?
I can do it.
Sure. Okay, Logan. Do you want to maybe just open up a new VEX code document or a VEX code project, just a new text project, and
I'll share my screen.
yep.
You can see it.
Yep, we can see it. Do we want to do this as a function, or not? What do you guys think?
I guess we could try it.
Yeah. Okay. So what's the first thing we're probably going to do anytime we have our code? I think Logan's on the right track there. Yep. Yep. And I think that's probably all the devices we'll need, right? For this. Left motor, right motor.
I think when I was reading the assignment, it also had an R, like it
Oh,
was
yeah,
moving
at this
forward, put
point-
an arm up.
Yeah, that's right. It does, because it does have something where you have to raise and lower an arm to simulate shooting the basket. Is basically.
All right.
Okay, so our first question is, do we want to make a function? And I say let's go for it. Let's make a function.
All right.
And if we're going to make a function, let's kind of talk about what we want this function to do. So what do you guys think you would want in a function? And do we want to make multiple functions, or do we want to try to do most of it in one function?
So basically, the function is going to be kind of like a loop that's going to have conditions or scenarios in it that can be adjusted without having to write it like 4 to 5 times. Like this function will be established as this while loop, and this one will be as this while loop, and you can just basically write the function itself, right?
Mm-hmm. So what do we want the robot? Do we want to write a function just for it to go forward a certain distance by auto straightening? Or do we want the function to actually have it go forward and back all at the same time in that same function? Or do we even want to write it so that the function goes forward, back, and does the shoot all in the same function? Or do we want to have those as separate functions? So how do we want to approach it? Because we could just do like the whole leg in one function, right? Because we could go forward and go back and then shoot, and that all be that function, and then just do it again for another set of values. What do you guys think?
This one's supposed to, it's like a suicide drill and there's a shot at the end of each one.
Yeah, that's
Then yeah, I think it should be the full leg, and then we can just manipulate the, one function would be the full leg, the moving forward, shooting, moving back.
Mhm.
And that's the function that we can just manipulate the values inside of it.
Yeah. Okay, so what kind of variables are we going to need for this then? And what do we want to call it? Call this function?
Don't you need it to go like forward and back? What is that, distance maybe?
Okay, so we'll need a distance. What do we want to call it first though? We probably need a name for this function.
Yeah, I think dist, like we've been kind of working.
But aren't we going to use that for one of our parameters for the function though? Or are we not?
So when I do a function, do I have to do the integer in front of it and we do a function like that? I'm not sure how. I've never done it.
Yeah. Okay, that's another thing too. What are we trying to get out of this function? Like, what's it going to return? Because that's going to determine our variable type. Do we really want anything back from the function? We just want it to do stuff, right? But we're not like getting any numbers back once it's done, right? So since it's only doing things, the variable type we're probably going to use is just void, which means it's not going to return anything. So instead of int, we would just say void. Yeah. So that's when you run a function and it doesn't spit anything back out, and that's what's going on here, right? Because we just basically want the robot to move, but we're not going to return any values back. So we'll use void.
Should we also include those variables like we were looking at earlier, like the fast speed and the slow speed?
I feel like those could be parameters for our function, right?
Oh, okay.
Yeah, because that way we can adjust them if they're not working out well, or we could even adjust. It is true that fast speed and slow speed, we're probably not going to change between things, so they don't necessarily have to be parameters, but they could be. Either way.
So I just want to make sure I'm understanding. So we're still going to declare the variables, but we're going to do that inside the function. What we're doing right now is like global variables across the whole code.
Yeah. So right now we're just declaring the function right now. So we're trying to think of a name for the function. Could it be just drill, or would that be a good name for the function, or suicide, or
Drill works.
Okay. Okay, so that'll be the name of our function. So now we need to give the parameters for the function. So I guess that's where we're going to open up a parentheses. And so we know for sure we probably want the distance to be a parameter that we feed in, right? So yeah. And it's like kind of DJ said, we could have parameters for the fast speed and the slow speed, or we could just make those global variables and not worry about putting them in the function. It might be just better off to put them inside. Now we don't actually have to, we're not going to assign it anything there. So we could just say int dist, and that might be all we need, right? And we'll we'll just make the other ones global variables. So we're gonna open up like a open and close a squiggly, and we're gonna put our code inside that, right? Let's go ahead and declare other global variables outside the function though. So we'll have a fast speed and a slow speed.
Yeah.
And we'll also go ahead and assign those values to, I think in the slides, it was like 50 and 40, I think 50 for the fast speed and 40 for the slow speed. And of course you can have your kids play around with those values too. Like for instance, the further apart the numbers are, the more it's gonna wiggle, I guess you could say, when it's trying to adjust. And it's nice that Logan is making these comments for everything. We do want to try to encourage our kids to do that because they will oftentimes not comment anything. Okay, so what do we need here? So I think the first thing we need is that loop, right? And we're going to put everything in the loop. Yeah. So and now we got to make our conditions. So we know we want to take the absolute value of our motor position, right? So and it's FABS actually. Yep. So, and then we can, if we wanted to, we could just drag that in. It's under sensing. And it's motor position degrees, I think.
This one right
Yep. It would actually go inside of.
here? Yeah, I was trying to.
Yep.
So there's parentheses around it, but they're
Yeah, we need one more parentheses, I think. I think we need one more closing because we have 3 opens and 2 closes.
I'm looking for right here.
Well, no, we just need another closing parentheses on the end, I think, right?
Yeah, one more on the end.
Okay.
That's weird.
But so now we gotta set our condition. So it would be after the second closing parentheses.
I'm sorry, what was that? After the second closing?
Yep.
So right here?
Yep.
What do I need to do?
Now we need our conditional, so like a less than, right? I think. Yep.
Yep.
Oh, I know what you said. I know what you're talking about. Less than how much?
That would be dist, wouldn't it? Because that's
Mhm.
Okay. And then we have to put also for the right motor as well, right?
yeah. So we'll have to do and, so double and sign, and that's still like inside that parentheses.
Inside this room, yeah.
Yep. And then I guess the quickest way maybe to copy that. Yeah. Yeah. Let's see. Let's hit build just to make sure that there's no errors in that. That's another habit I would suggest you teach the kids is to run that build, make sure there's no errors, like, and not wait till the very end and try to troubleshoot everything. I do realize that we actually are missing something that we need to do before our while. Does anyone remember what we should probably do first?
Set the encoders to 0.
Yeah, exactly right. So we probably want to set those encoders to 0 first. So so before our while loop, but inside our function,
Right here.
yeah,
We're
I
gonna
guess
set-
we, yeah.
ahead.
So we just say, I think we just say left motor position degrees, kind of like how you have it. Or,
There it
It's
is.
right here.
oh yeah, motor set position, sorry.
Motor set position.
Right after stop.
Right here.
Right after stop,
Right after stop. There we go. I'm on the wrong one.
yeah.
And then we
And
want to
then
do the right as
Do
well.
it
Right?
again for the right motor, yep. And Beverly, is this making sense so far?
I'm following. I'm trying not to be too lost. I'm looking at like the parentheses and I'm just trying to see where one opens and one closes. So I just have to make sure I match up.
You guys probably gotta pick that stuff up for their first.
I gotta match up what parentheses works with the other. I can kind of see it. And you're right, it's just the fact of doing it myself that it can sink in like the other things have started to because I'm going through the motions.
Okay,
I do have, I'm trying to look back at the coding to the side. So it was first he dragged in and then he started applying. So I just have to remember to go to that sidewall where it says under code.
okay, so, okay, so we've made our while loop. And now we just, so I guess we need to put our conditions that we're doing, right? So I guess next would be our if statements, right?
The vendor. Oh, I guess we'll, there we go. Yeah.
So, so what do we want our first condition to be? Like if the left is less than the right, or?
Yeah,
Uh,
sure. Either that or right is
Less.
less than
Alright, so that's
So you could maybe, if you wanted to, you could just copy that, because we want to keep the absolute value stuff too.
Mhm.
okay.
Yeah, so you might want to just copy that fabs, yeah. Yeah, we don't need, yeah.
Also, do I need this int main down here at all?
Yes, you
Okay.
do need the
Alright,
end
just
main.
make sure.
And so we could say do you
Doing
want to do less than or greater than?
I guess we do greater than.
Okay, and then copy the, yeah, or,
I guess it should be. I could be using my something else. Let me see if it said it.
well, I mean, that's fine. I think your left motor has an extra T in it though.
It does.
Well, you already have it now, so
Yeah, no, I'm just I'm gonna set it for the next one. So
okay. Well,
Right.
you can literally copy that whole if line then, and then just change the sign on it.
yeah. Well, I'm using my Windows key V and I can paste individually like what I want.
Oh, okay.
Ooh,
Yeah, if you do Windows key V, you have your clipboard and I have my left motor, right motor.
Okay,
Alright,
so
in
what
the
do we
if
want to
statement-
do in this case? So So basically we want to do motor spin, right?
Mhm.
So we'll do, see, motion,
Yeah.
we'll do
And we wanna-
percentage, right?
We
We're
won't
gonna-
spin 4, right?
We won't use spin 4. We're just gonna use spin.
Oh no, it's just spin. Yeah.
Yeah. And yeah, and instead of using voltages, we're gonna say percent.
I can't remember what the acronym for. Isn't it like a?
What's that?
It's
There,
just the full word.
Isn't?
yeah,
Mhm.
yeah, it's just a whole
I
word.
thought it was PR like CT or something. So if the right motor is greater than the left motor, this needs to be 50 and the right motor needs to be 40.
Yeah, but let's use our variables.
Okay.
That we, so we'll say fast speed and slow speed.
So we do fast speed.
Mhm.
All right.
Okay. So that's one of our things. So then we can say else. Yeah, you could just copy all of that. But else if. And I think we need another closing curly, if I'm not mistaken.
Yeah, we do.
For some reason, by not having the numbers inside the lines and he's using fast speed and slow speed, it almost seems, I don't know, comforting a little bit instead of fighting with numbers. To what
Yeah.
I'm looking at.
Yeah, that's another nice thing about it. So okay, so you see what he's done so far. So he basically copied what he had, but he added an else in front. And then he also swapped the greater than to a less than. And then
And then
So-
this will just be an else, right?
yeah, it will just be else. You don't need any conditions on it else. So well, yeah, you could just say else, yeah, and then just take out all the conditions. In fact, you can't have a condition for else.
So I need to take out the conditions.
Yeah, take out all the conditions. It's just else.
There's no condition at all for it. Okay.
And
And
let's
they need to be at the same speed, right?
yeah.
So do we have like a regular speed, I guess, when you said it? Like,
Well, that would be fast speed, I guess,
okay,
right?
just post fast speed. Okay.
And
Yeah.
let's see if that compiles. I think there's error. Okay, do we not match up somewhere?
This will unexpected parentheses.
Need another closing parentheses on
Yeah,
line
so-
77.
77, another closing.
Well, we don't want to close that off. I mean, yeah, we don't want to close it there. We need to, but we do need another closing process to match up with that open one. Not
What
process,
the-
but squigglies. If
Oh, these guys matched up right here. This one.
The if statement's not closed.
The if statement's not closed.
well, that should close that if. Yeah, so I open the if, close the if, and then we're opening up the else if and closing the else if. Then we're opening up the else, closing the else.
It's a normal parentheses, not a curly bracket.
Right here.
Yeah, before that, put a closing parentheses.
Okay.
No? Yeah, one more. Oh, we have another problem earlier on. Oh, it's
Right.
before the greater than sign. Right, it's right there.
Okay.
Uh-huh.
Now you might have to delete the extra one that you put on there. Now there's still one more because of the if statement.
Wait. So I know under we need to close the fabs thing for the right because that's not closed.
Yeah, close that one and then
And then,
go add another one that one's not closed.
yeah, this one needs to be right here.
Yeah.
And that's probably for
Yeah,
all
that's-
of these.
Yeah.
Because we copied and pasted.
Got you. Okay. Close those together.
And luckily Elson have, oh, so will it build now or? All right, that's
That's
great.
it. Okay.
Okay, so once we're outside of our while loop, we do want to stop the motors. So still within the function, but outside the loop. So that's outside the, that's, yeah.
This is within it. Let me close this so I have more. So this is the first beginning of the while loop. This is the end of the while loop right here. So
Yes.
in this space right here.
No, that would still be inside the while loop.
Okay, so we want to be out. So outside the while loop. All right.
Yeah, we want to be outside the while loop. Yep.
So right here.
Yep.
All right. So this would be.
So we just do like motor stop for each one. Yep.
Motor stop. Where you at?
Okay. And if we're doing the whole routine in this function, I guess the next thing would be to move our arm up and down.
Mhm.
So you could just use, there's no reason not to use spin for the arm. So this would be after, yeah, after stopping the motors.
So we're trying to move the arm, you said?
Yeah. I don't know, like you could do like a 180 degree, yeah, and you could just, yeah.
All right. Oh, I'm gonna put it right there. And this needs to be arm motor.
Yep. And we could do it 90 degrees. That'd be fine. But after we raise it up, we do want to also then lower it again.
Yeah. So I can just do negative 90 degrees underneath it.
Sure. Or you could change the reverse. Either way, it would do the same thing.
Now,
Okay.
do we need to set like the position of it as 0 to begin with, or are we okay? Or could we?
I mean, it defaults to 0. I mean, you could
we set it?
do a set position
Just
before.
to be safe, I guess?
Yeah. I guess to, yeah, I guess to be safe, you could. Yeah.
That'd probably be smart to avoid, like, if this is repeating over and over again, if it doesn't go all the way down.
Yeah. Yep. Okay. And I guess now we need to move back, right? It's because we might as well do that all in the same function. So I guess that's going to require just copying all that, right? All the while, starting with the while.
Okay, so we copy our whole while loop and then just paste it underneath our arm motor.
Yeah. And we'll have to make some changes to it, obviously.
Yeah. Let's see. I think that was the bottom of it.
What I find more efficient is taking Apollo screws and sorting them by size and then figuring out what size they have.
That's what I do. I now have a pile to compare.
So, what's the only change we need to make then?
Is it our less thans? Or like our,
Well, remember, we're using absolute value, so we don't really have to mess with that. I think it's
Okay.
just changing our forwards to reverse, right?
Yeah.
Yep. And it built. That's good. And then we got to stop the motors at the end of that too, right?
Does it need to shoot also? On the
Uh,
other side?
No, I think it's. Well, are you supposed to shoot at the end of going back, or are you supposed to shoot?
Let me go get the assignment and look at the assignment real quick.
So we might need to move this whole thing.
Yeah, the shoot might be at the very end of that. Yeah, maybe. But we definitely want to stop the motors. Yeah, it depends on where you're supposed to shoot. Are you supposed to shoot? Because typically in a suicide, don't you go forward, then come back and then shoot?
I didn't even know you shot it all on the suicide drill.
I was in band, so I don't really have any context for you.
Those drills are just back and forth.
Yeah.
A lot. You don't do any shooting.
You don't do any shoot.
Not on normal suicide drills, you don't know.
Yeah, in a normal one, you don't. But
If I had to guess, it'd be on the back because you're probably running underneath the goal. You're running
Yeah.
out, coming back. So
that's true. So we probably just need to move that, to the end of that.
So in the assignment, there
Mhm.
it says that it wants to travel 2 feet forward, 2 feet back, pause for half a second, and then shoot. Lower the arm and then do 4 feet, 6 feet, like then kind of repeat the process, but changing the.
Okay, so I guess after the motor stop, but before our arm raising, we just need to add a weight.
Mm-hmm.
okay, so it will. Okay, all right. So we'll add a weight.
It's under control.
Okay. Weight.
It's at the very top. We don't. Yeah. And it said wait for half a second.
That's what it said. Yeah.
You probably want to do it as 500 milliseconds. So
That's what I
500.
was gonna do. And we'll do. How do you do milliseconds in this one? Just
MSEC.
okay. I could. All right.
And couldn't we also up on the global variables put a wait time or define the wait time as a certain amount?
We could.
You could have done like a float wait time.
Hmm.
Like this.
Yeah, we could have if we wanted to. I just from experience of running this code, the robot will kind of jerk and kind of get off course when it's going from forward to back each time.
Mm-hmm.
So it actually kind of helps to actually have wait times in between the going forward and the going back as well. I would probably also add a wait there as well. Like so between our two while loops.
So like right under motor stop right here.
Yeah, right after motor stop up there, I would also throw in a wait. Even though it doesn't say to do it in the code, just because anytime the robot is like, or the motors are quickly swapping directions, you'll have the robot kind of jerk around a bit, and it could just end up getting off course. So having that little bit of weight kind of gives it a chance to kill the momentum before going back again. Okay, so it looks like we have a pretty good drill function. Now, all that's really left is to use it, right? Now, should we should we do the math to figure out how many degrees we need that motor to spin? Are we assuming that we have a 1-to-1 gear ratio and 4-inch wheels?
Makes it easier.
Okay.
Yep.
All right, so if we want 2 feet, that's going to be 24 inches. And just doing the math here, we know no, it's going to be 4 pi inches for every 1 revolution or rotation. And every 1 rotation is 360 degrees. So I believe the math works out to be, so we should do 24 divided by 4 pi. And then times 360. Looks like that should be about 688 degrees is what I got for 2 feet.
That sounds right. That sounds good.
Okay. So now we just got to use that drill function. So we're going to put that in the int main, because int main is where everything gets run at. So
now we just got to do drill.
Yep.
That's how we're gonna call it.
Yep. And we gotta call it inside our int main.
All right.
So we should just be able to say drill and 688 will be our
equals 688.
no drill parentheses 688, because we gotta that's where we're feeding in our parameter and semicolon, and that's it, right? So that'll be our 2 feet, and then I guess our 4 feet would be twice that, which would be
1376.
Yep.
1376, you said?
Mm-hmm.
And then 2064. And then our last one would be 2752.
And say it again, sorry.
2752.
2752.
Or, we could have just said 688 times 2, 688 times 3, 688 times 4 if we didn't want to do our math ourselves.
I don't like the way it looks.
I personally am fine with having comments out to the side.
For me, like, it doesn't look very organized.
Hmm.
I don't know, it's just weird out to the side. It kind of helps me split it up if it's above it.
Yeah.
I don't know, it doesn't matter.
Yeah, everyone has their own habits, right? Yep. So hopefully this will build.
Yeah.
I would like to see this run. Do you have a robot you can load that on?
I have mine, but there's something up with my like my right motors are not working right. Like they're not. It might be that it's in a bad port, so I could try. I can see if it'll work. Let's see.
Do you know how to check to see if your motor is working on the brain?
Say it again.
You know how to check to see if your motor is working on the brain, right?
Well, I know it worked. It worked fine. Like they do work, but like it was like it wasn't calling it correctly. I don't know, but how do you check it?
On the brain itself, if you click on devices, then you can pick the motor,
Okay.
and then you can press the forward and back buttons to get them to run, and you can just kind of check to make sure they're running.
So we said the left motor is going to be.
I think he had left in port 1 and right in port 2.
Yeah, I'm just swapping the ports real quick.
So this is probably a dumb question, and maybe I'm just confused. My brain's not working. But so because we did all the while and if and all that, I kind of understood why we were doing all that. But we did all that before. Then now when it gets to int main, it's just going to run with these values instead of.
Yeah. And once again, we didn't enter. Functions actually get introduced in the next chapter, but basically we wrote that function called drill, and so that every time when we call on drill, it does everything in drill. And so we had all that code in drill, and so every time we say drill, then it's and we feed what number we want for the drill, and so like that 688, that refers to that dist, because that's the
Right. Okay, yeah, I think I understand. Because I noticed when I was doing it before, yeah, it's like forever long if you keep using all of it. So this makes sense. I just had never seen the like function used before, but you said that's the next chapter.
Yeah, and that's why we did it this time with functions, because like you said, if we didn't use that function, we would just have to copy all that, and it would be, we've already got like over 100 lines of code here, and that would
yeah. And I
would,
noticed, sorry,
no, go
whenever
ahead.
I did the basketball drill before, like, and I saw exactly what you were saying, where like I felt like I needed to stop between each thing because you're right, like it's like because of the inertia, it wanted to like keep going, and then I also thought about the fact that like I think one of y'all were talking about adding weight to it, and I thought maybe because it was unbalanced because it had the arm on it, like maybe that was part of the issue of why it was kind of like tilting and jumping a little bit. And so I think because my degrees, like theoretically these should work, but mine, it wasn't working where like you just double it and it worked. It wouldn't go all the way back for some reason.
Yeah, that's true too. Theoretically, it should work if you double, but because of the momentum and stuff like that, it wasn't exactly. So yeah, yeah.
Well, and wouldn't, I mean, this is that accumulated error thing. Like if it even turns one tick too much on one run, that's going to get magnified every single time it repeats.
Yeah.
That's exactly what it was doing. You're exactly.
This is also why, if you want to take a step further, if writing code to make it as it's approaching slow down, really kind of gets rid of that jumping around error, because even with the weight, you'll still have a bit of a jump sometimes. Also, it kind of depends on how you have your brakes set too. So there is a brake type. There's 3 different ways the motors can brake. And there's a command for set brake type for the motors. So the 3 types of braking is coast, brake, and hold. So coast is basically when you tell it to brake, it is basically just cutting power to the motors and it'll coast the rest of the way. Brake will actively run the motors in reverse to brake. And then, but once it's stopped, that's it. It doesn't run any more power to the motors. And then hold will actively try to hold that position. So hold is really useful. Like if you're like, say, raising an arm and you want to keep the arm up, it will continuously run power to the motor to maintain that position. If you use hold on the robot, the drivetrain base, what you'll see is if you're running it and you have hold, even if you push that robot a bit out of place, it will try to go back to place. So because it's trying to hold that position.
So when you just stop the motors, what is it like? Is it not using any type of braking or?
I think the default is brake. But you can change it to coast or hold if you want to. I think, but I believe it defaults to brake. And that's where it's actively trying to stop. Okay, so I see we've got it built and downloaded. Do you want to not share your screen anymore or?
All right, yeah, I got it on the program. I think I did the test with the motors, and one was spinning the opposite direction the other one was. So maybe it had something to do with the program or whatever. I don't know. But I put them on port 1 and port 2, and it seems like it's going to work. So
Okay.
I need
So-
to get some space to do it.
So they're spinning in opposite directions?
No, they're good now. They're good.
Oh, okay.
now. They were spinning opposite directions, which I think is just because it wasn't set up with a program. So it's going to make sense because they're in different positions. But
So do you have your robot like off the ground or?
say it again.
Do you have your robot kind of off the ground and was just running it?
It's on the ground now, but yeah, I had it off the ground. Yeah.
And did it seem like it would like go so far and run them backwards and then twice as long and backwards and
Yeah, I can probably put it in my hallway and see if it'll run.
yeah, I wouldn't mind seeing what it does.
I thought I had another cable for the motor in my bag, so I can just put the arm motor on top. I don't have the arm motor set up like I have an arm built.
Yeah, I mean you could, like you said, you could just plug in the
Yeah.
motor.
That's what I
Yeah,
was trying to do, but I don't know if I have another cable though. I have an EXP motor that might work. That'd be kind of weird.
right. Yeah, I mean, it wouldn't matter if you had an EXP motor or not. I think the code treats it the same. So
I could have sworn I brought an extra cable here, though. I guess not.
Hmm.
All right, I'll just hook up the EXP motor on, I guess. Shoot, I don't know. Would it give me an error if I don't hook it up at all? Or
I don't know.
I don't know. This is
I don't know how it will execute the spin 4 command is the only.
Well, I just realized something. I don't need a controller for this, so I don't need to.
Yeah, you don't need the antenna wire.
Yeah. So I'm just gonna. All right, I got it set up. Okay, let me go ahead. Maybe I can join the Zoom on my phone.
Yeah.
That'd be easier so I can see it.
Yeah, I was doing that yesterday.
Let's see.
Could you turn off your screen share?
Oh yeah, sorry.
Was everybody able to type in as Logan typed in? I've been kind of sidetracked over here, and I wanted to, type it in and see if I could try it out on my robot, but I still need to hook a wire because we're using the arm now, right?
Yeah. And you don't, yeah. So yeah, you would hook a wire from your motor on your arm to port 3 is what we have it currently set.
Okay. Because I think mine would work. I mean, it's been okay so far with the twist ties. I actually have the school board calling me, a coworker texting me, grandbabies running around the house. So it's one of those days I'm like, do I take off? But I can't afford to not take off. I mean, I can't afford to take off. I want to stay with this.
Recording in progress.
All right, and we got Logan on. I better stop talking because it sounds like echo.
Yeah, I can.
Logan, you should mute your laptop.
I thought I was muted, but
There you go.
guess not. All right.
Can you turn on your video?
Let me get my hallway and I'll. I don't know how far it's gonna go.
Well, if we did the math right, it should go 8 feet.
That should be good. All right. Trying to. 1 second. All right.
It didn't go backwards,
It's kind of snaking.
and it didn't go reverse.
No.
Y'all, the other day I put in I meant to put in 1200 and I put way too many zeros and that thing was just going. I had to chase it across the room.
So yeah, so the wiggly stuff, that's the auto correcting working. Why is it not going backwards though? Is the question. So yours just went off on you, huh?
Yeah, I was I'm chasing it, trying to hit the stop button because it was just gonna keep going. But yeah, I'm sure I'm not the first person to ever do that. But
I guess we need to. So we need to look at our code and figure out why. So the reverse section of the while loop, I guess, isn't working, right?
Yeah, that's the issue. It's not. It's just going forward, and then it does the arm, goes forward again, does the arm again, goes forward again, does the arm, and it just keeps going. I don't know.
Is it doing the arm after each set or after each other set?
After each set.
Okay. So that means So that means it's just ignoring the backwards part completely then, right?
That's gonna be the code.
I know why. I know what we need to do. Okay. Yep. Would you mind sharing your screen again, Logan?
Yeah, 1 sec.
Has anyone else figured it out yet?
I don't know what we put. I gotta see the thing again. But did we put else? Maybe we used the else wrong or the if wrong.
Yeah, I can't remember the code exactly.
I figured it out. I know what's wrong. I'm really sure.
Sorry, I was trying to turn the volume off on my phone, so there wasn't a double echo thing going on. So I got it. Can you hear me?
Yeah, we can hear you just fine, Logan. Okay, so I want you guys to kind of figure this out because you guys are smart. What do you think went wrong?
Okay, so it's ignoring the second loop.
Mm-hmm.
Okay, so there's some issue where we have to create a scenario where it's gonna read the second loop. It's not ignoring it because it traveled 16 feet because it didn't come back. So it's not coming back to us.
How big is W time?
It's half a second.
Okay.
Oh, well.
That's just for a pause though.
Yeah, it's that.
Where do we set it?
I set up here at the top.
Okay, so it's tiny.
Yeah, and he called it a flute. So
it's got to be, yeah.
So the condition must be false to begin with.
Mm-hmm.
If it's not happening.
Yeah.
We didn't reset the position to 0.
There you go. That's the problem. Because we were already at that dist value. Because we had just run the forward and we were at that dist value, right? So we gotta reset the positions again before going back.
Dang, that didn't take long, right? Man, that's great.
Yep.
All right, so let's go ahead and try it again. Yeah, I definitely see why plugging it into the controller is so much better than the brain.
Yeah. Yep.
Okay, so it's connected. And then connecting online is kind of annoying because it
Yeah, you have to do that every time.
it gives you 2 ports, and then if I pick the wrong one, it's like, I don't know, it doesn't automatically pick the other one.
Yeah, you got to try the Vex 5 Pro. It's so nice.
We have it, and all of my students use that on their computers, and we have a company portal or software center, and we can get to it, but for whatever reason, like, I can't get to it on my computer.
Oh,
It's not available. I don't know why on my teacher computer. I don't know. It's weird. Okay, so it's on there now. It's downloaded. So let's go ahead and see if it'll work. Sorry. All right. We go ahead and
We weren't resetting the encoders again, so it was already at that value.
All right, so let me go ahead and okay. Let's go and try it again.
All right. I see you got your dog.
Yeah, that's Gus. He's a little Yorkie. All right. Okay, so that my fireplace is well over 8 feet, so it should not come by us at all. Can everybody see everything? Good.
Yep.
Gus, come here. Okay, now it's going.
Yeah, it's
There, it's
probably
working now.
mm-hmm.
So it's going there, it's coming back.
4 feet. Yep. And it's kind of doing that funky autocorrect.
Yeah. My dog trying to attack it.
And this should be the last run.
so depending on the little waggles and where it stops, it just keeps getting further and further off from a straight line.
Yeah.
I was about to
Yeah.
ask you, did it have a sensor? Because it missed your chair. It did pretty well avoiding that chair.
Yeah, I don't know if it's my wheels might be a little loose. They're not the tightest. I did build this pretty quick, so I wasn't trying to do it. But you can't hear it, but it is turning the arm motor. So this is the motor I've hooked up. It's just connected, and this is the arm motor. So it's kind of it was working though. So, but it worked that time.
Yeah. And this also shows us why it's important to run our code and not just assume it works. Because you'll kind of miss little things like forgetting to reset the encoders and things. So and we could tell it was trying to correct itself, right? Because of all the wiggling. Now I will say that's probably not the best way to do autocorrect, but the reason we do it this way for the course is because it's more to teach the kids about using loops and also using if statements and stuff. The better way to do it would probably be a proportional control. And I think we talked about that yesterday, but once again, that might just be a little too much for our intro class. But then you would get a nice smooth auto. It wouldn't be wiggling at all. It would be really nice and smooth.
It's still a pretty fun, like, little activity though.
Yeah. So that's the majority of Unit 8. So that's probably the most technical of the units that we've done so far, right? Especially when it comes to the programming. And there's so what I want to say about that, if they can master Unit 8 and be able to do that coding, I think they're in a really good position. I mean, I feel like if they can do that, then we probably accomplish our objectives as far as like this class goes, in a way, you know. As far as like introducing them to coding and the if statements and stuff like that, and then we've already kind of gone over that over building and stuff too. So if you can at least, if your first year kind of behind for whatever reason, maybe because you're not getting your parts in or whatever like that, if you can at least get them through like that unit 8, I think we're probably pretty good.
And if they, I mean, the next unit is just incorporating functions and sensors. So
Yep. Yeah, exactly. And so the rest of it is just sensors, but once again, the encoder is a sensor, right? And so really when we're incorporating these different sensors, it's really more the same in a lot of ways, at least as far as the coding goes. So you'll still be using like ifs and stuff like that. Like you might like run, well, of course we're going to look at it tomorrow and stuff, but like in the case of bumpers, you know, you're just doing like if bumper's not pressed, you're running forward or something like that. So let's see. Let's see. So we kind of I think we've accomplished what we're supposed to do for day 8. It looks like there is a whole group meeting again at noon. If I'm reading this right.
it was
It got
canceled.
Yes, they
That
canceled
one
it.
was canceled too? Okay.
Mhm.
So we just haven't had any luck with those. So okay, so the new meeting is canceled. Okay. In that case, looking at this, I think we've completed our objectives for today, right? We've done the unit activity, going over the while loops and illustrating code. So tomorrow, we'll be looking at the button sensor and the ultrasonic sensor. Yeah, so looks like we're moving along pretty well. I think also in unit 9, the button sensor one, we also introduced how to do random numbers. So because one of the activities is trying to make the robot perform like a Roomba. And so the idea is for it to like hit a wall, back up a little bit, and then turn a random amount before moving on again. And so we show how to do a random number and with the vex stuff. And it involves like doing a line to generate a random seed, and then and it kind of gets that random seed from using the timer values. Those of you in computer science, you kind of know it's actually really, really hard to generate a true random number. And the way we're kind of doing it here is just using the timer to a really, really high precision and using that like last digit, because so that digit's changing so fast that it might as well be random, because anytime you grab it, it's gonna be different probably. But even then, it's not really a true random, but it's enough to for our situation at least. Okay, so I think we might be done for today. I know it's only 10:30, but if you didn't finish that program, I would recommend everyone else try loading that program that Logan did and running it on your own. And then if you're running into problems, like try to troubleshoot it too. And you can, I would say you could go back and look at the video, but I don't know how long it takes for Vanessa to post them, because it's got to compile first. But everyone
Once
else,
it's loaded, I definitely will do that. I will try it out for sure. It was a lot there. I don't know if it was more than the other things we've been doing. Oh my goodness.
it's the most complicated code we've done so far, I would say. But Logan did a great job with it. Yeah, so
Thank you.
okay. So I guess we're gonna call it here. If you want, I can leave the line open. So like if you guys want to work on your if you want to work on that code,
Eric, I have a question. How, because I don't know the PID control, would you mind just doing a quick run through of how
Yeah.
to do the same thing with PID?
Sure. Okay. In fact, yeah, great. Yeah, that's great. In fact, I kind of I put some resources in there. There's an optional folder I kind of added that has some information about PID, and it's got some sample code. Like, I'll share my screen, but yeah. So in the auto straightening, there's this optional PID folder, and it's just a folder I made that had like an optional assignment. And this assignment is so this is like one of those activities where we're trying to create a kind of a smooth motion, and so we kind of like broke it up into 3 sections. So basically if you consider your motion, we have like an acceleration phase to the motion, and then a going constant speed, and then a deceleration phase to the motion. So let me see. I'm trying to remember what code ended up posted here. I'm gonna try loading that code. Let me download it because I don't remember what this code is. And let me load it in VEX Code.
Yeah, I think that would be helpful, just walking through what the code looks like. I think I could grab on from there.
Yeah, and we can let me just see what this example code is.
And then 1 second, the function writing, because like I don't think I'm going to remember all of what we did. That's in which unit, so that I can look back at it while I'm kind of going over it.
The function writing is actually introduced in Unit 9. I'm really positive of that. Let me make sure that unit.
I verified. I went back and looked at Unit 9. It's in Unit 9.
Okay.
Yeah, so the kids aren't really going to use a function in Unit 8.
Well, like I said, I just because how tedious that other assignment would be without, I went ahead and introduced it to my kids early.
Okay, all right.
So if you want to, you can.
And we did functions in the intro class for that Morse code device. I showed them how to make a function for a dot and a function for a dash. So, and all of those kids took intro with me. So,
yeah. So they're okay. So I haven't looked. Even though I did write this code, I haven't looked at it in a while. I tried to comment it as much as possible. But so okay, so basically here's a function called drive forward, and it's taking in a distance and a speed. And then we have these 2 global variables we got declared. One's called error and one is called KP. K is just a constant, and the P stands for proportional. So oftentimes if you look at PID control, so they'll have a constant, and that constant just basically adjusts like how much an effect you want that particular thing to have. So the bigger that constant is, the bigger of effect the proportional will have, or the integral part will have, or the derivative part will have, if you have those variables. So basically you adjust this to meet what you want, but we'll walk through this. Okay, so let's look at this function here. So this function is similar to what we were doing before, but I don't think this has any auto straightening in it. This is just going forward. But let's see if we can explain what's going on here. So we're taking a distance and a speed in our drive forward function. And then just like before, we're resetting the motor positions, setting those to 0. And then here is our loop here. By the way, notice this function is a lot smaller than the other one. So in this case, once again, this is just like what we did with the other. As long as these are less than that, it's going to run the function. Less than the distance is going to run the function. Okay, so the first thing we're doing is calculating what we're calling the error. And the error is just the difference in between the two motor positions. So so if they're, say, if the both encoder counts are 100, then the error is going to be 0. Otherwise, if the left motor is ahead, let's say it's 110 while the right motor is 100, then the error is going to be 10. Or if the left motor is 90 while the right motor is 100, then the error is going to be -10. So that error is just telling you how different the two encoder values are.
And I like this because it's like we don't have to try to calibrate like the 40, 50 or whatever.
Yeah.
It's going to be a real time what the difference is between those two motors.
Okay, and so yeah, so after we calculate the error, then we're going to run our spin commands, but to adjust the speed, so we have that set speed that we wanted, but then in addition to that, with the left motor, we're going to subtract out the error basically, times that KP value. So that KP value is going to times that error is going to be how much we're adjusting the speed. So for instance, let's go through some situations. That's probably the best way to kind of understand it. So let's say our speed was set to 50. And let's say that our left motor and right motor were the same. Okay, so we got the same encoder values on both. So so our error is going to be 0. And so in that case, the left motor is going to run at speed at 50, and the right motor is going to run at 50. And so they'll just be going both the same speed, which is what you would want if the error was 0. Okay, so now let's look at a situation where let's say the left motor is at, say, 120, and the right motor is at, say, 100. Okay, so what's our error going to be in that case? It's going to be 120 minus 100, so our error is 20. So what that's going to do then is, so we'll have a speed of 50 minus 20 times 0.1, so 2. So that's going to make our left motor run at 48, and our right motor is going to run at 50 plus 2. So it's going to run at 52. So our left motor is going to be slightly slower now, and our right motor is going to be slightly faster now. And that's kind of what we want when, in that case, the left motor was ahead. So we do want the left motor to slow down and the right motor to speed up. Now, let's say if it's a really big difference, like let's say the left motor is at 200 while the right motor was at 100. So in that case, our error is going to be 100. And so what we'll have is our left motor speed is going to be 50 minus 0.1 times 100. That's going to be 10. So that's going to drop our speed down to 40 for the left motor. And our right motor is going to be 50 plus 10. So it'll be 60. And so as you can see, the bigger the error gets, the bigger the correction of the speeds get. And so and that's really what it's kind of all about there. So what you would see if you run this auto straightening is you wouldn't have that wiggle at all. Instead, what's going to happen is if it's off a little bit, then it's just going to correct a little bit. It's not going to overshoot. And so if it's off a lot, then it's going to correct a lot. And that's what we refer to as proportional control. So and proportional is just one part of PID. The other part is like integral and derivative. If you're familiar with math and calculus, you might remember that integral is like would be like an accumulated error. And so you could also have a thing where you're actually let's say for whatever reason, for instance, let's say it was drifting off course and it continued to drift off course for a long time. If you have an integral component to it, the longer that it's off course, the more that integral component is going to build up. And so you would have, so just like how you have the speed minus a KP times error, you would also have like a you would have like a KI times total error, something like that factored in too. And so as that accumulated area increases, so that would be your integral portion, and so that could have an effect. And then the derivative is kind of used. So the derivative, if you can kind of think of it, if you can think of all of these as like a graph, like graphing the error, then and the integral part being the integral of that graph, the derivative part would be like the slope of that graph. And so what that can help with is smoothing out like overshoots a bit, because what that could be is if you're approaching your target at too steep an angle, what you can use is you can do that, look at the derivative, in other words, looking at the steepness of that slope and maybe lowering that steepness down a bit. Or adjusting it so it's not as steep as it was approaching. I don't know if I'm explaining it super well, but those are usually the three components, and they're used in all sorts of situations. Like pretty much almost all industrial machinery uses PID loops to adjust things. So there's I think I put a link to an article if you're more interested about it.
I think that article link is broken.
Oh, really?
Yeah, I tried to open it.
That's a shame. Oh, it was an article done by a Vex team, and hey, okay. It was working as of last year. It was working, but that's a shame that it's kind of. I guess I better find a better link then. But you could probably find. I'm sure you could probably find like a YouTube videos or something explaining. Maybe. Yeah, so there's probably like a lot of things, and you can probably also in terms of Vex, you could probably find a lot of teams explaining it too. But it's a really good way of smoothing out things, your motion, so you don't have, so you're not like overshooting or anything like that. Because basically can kind of adjust the speed as you're approaching the value. So you can probably find a lot of videos and stuff about PID control, but that's kind of more of an advanced topic. So, but I'll need to find a better article for it to post. It's a shame that link went dead, because I thought they did a really good job of explaining it, because they kind of showed out like different situations, like for instance, like of a drivetrain that had an example with an arm, and they even had like sample code and stuff too. So
it's pretty cool to hear this, because I didn't do much with the kind of controls. It does remind me of like a PID controller, like in industry and stuff. But it's pretty neat that the kids will get to see this, because it's always like, I'm never going to use this math ever again, or like, it's crazy that they're not even going to be exposed to integrals or derivatives until possibly college. I doubt they'll hear anything about it, but it's kind of cool that this is my first time of like actually hearing it incorporated into a real life scenario in the classroom. It's kind of neat. I like the way this is done.
Yeah, and it's kind of interesting when you program the integral, because the integrals of math, you don't really think about it, but when you're going through a loop in your programming, you can think of each cycle through the loop as being a slice of time, right? And so like when you're adding up the accumulated error, it's just like you're just keeping up with a total error as you're going through each cycle of the loop. Then you just, so like your error would be just so like for instance, for that integral part, it's just you might make a variable called total error. And it's just every time through the loop, the total error is just the total error plus error. And that's just keeping up with your total that way. And that's your integral.
It's
So
like
it's
an application using it. I mean, I guess they don't really see the math behind it, but it's a good example of like how an integral will work in a real life scenario, or in this scenario too. It's kind of cool.
Yeah.
Can I see the rest of your code, like the top of it and the bottom of it? I just want to look at it.
Oh yeah, I'll put it back up. And also this code is in this folder right here if you want to just pull it up yourself.
Okay, yeah, I'll do that then. That's fine. That's a lot easier.
But and this is just, yeah, this is just a basic this is for auto and this is for auto correcting here. But this is not for controlling your speed like we mentioned before. So I had the kids we kind of worked through an example of speeding up and slowing down. And basically the way that worked, so basically we did have like so in our kind of while loop for reaching that position, we actually used like an if statement. So like where you had like if it was less than a third of the position, then that would be the speeding up phase. And if it was, and else if it was less than 2/3 of the position, that would be the going straight phase. And then finally the last else would been if you were in the slowing down phase. And so and basically what you did was your speed was basically okay, like in the speeding up phase. So you had that third of the third of your distance, right? And so your speed was your encoder position divided by the third of that distance, and then times that target speed. And so as you were getting closer to it, then you were speeding up more and more. And plus, but also in addition to that, we had to add in a constant of like a little bit of speed, because otherwise you would never get going, because you would start at zero position, you'd be at zero speed. So you have to at least add a little bit of a speed to get going. We also found at the end of slowing down, you also still wanted a little bit of speed, because otherwise it might slow down and not actually ever reach its target value and get stuck. So, but yeah, I think the proportional control is really, really useful stuff. But it's just probably too much for a beginner course, an intro course. But if you have time for it, it's something that's used in industry very, very often. Like we had one of the parents is a process engineer at one of the plants here, and he came in and he was trying to explain how he like a lot of what he does is just tune those PID loops for the different machinery they have to make sure everything's running right. So, and once again, that KP, that constant, so you can adjust that to determine how much effect that error will have. Yeah. So, okay. I hope that's a good explanation. I'll stop.
No, that helped a lot. That was great.
Yep. But thanks for pointing out that link's broken. I'll try to find a better article to put there in this place, and maybe post some of those YouTube videos too. Okay, so yeah, our word for today was encoder. Yep. I'm just now reading all the messages here. Okay, so I'll stay on the line if anyone's having trouble with their code. But otherwise, just try running that code and seeing if you can pull off the basketball drill. And if you're having trouble, I'll be on the line for a while. Take care.
Have a good day.
Bye. See you tomorrow.
Thank you, you too.